In this tutorial, I work several proofs for you that include both inference rules and equivalence rules. So let's start with the proof you see here. So line 1 is not P and not Q. Line 2 is P or Q or R or S. And the conclusion we are trying to derive is R or S. So let's approach this as I've recommended. A good rule of thumb is to begin with the conclusion and ask yourself where the conclusion is likely to be derived from. So if you look at the conclusion, we have R or S, and we have two premises. Line 2 has R or S in it, so that is our most likely candidate. So line 2 is probably where we're going to get R or S. So what we have here is we have, just a moment, okay, so we have P or Q or R or S. So now if we think about this, the major operator in line 2 is OR. So we want to review the inference and equivalence rules that might allow us to manipulate this line. So one of the things that occurred to me is disjunctive syllogism. So the first premise of disjunctive syllogism has a major operator of OR, just like this. So if we think about this expression in a disjunctive syllogism sort of way, what we see is that the conclusion is actually that right-hand side of the first premise of disjunctive syllogism. So what would we need for the second premise? We would need the negation of this front end block, the left-hand side. And of course, what does that have in it? It has P or Q. So we'll put groupers around there to indicate that it's a single unit. Okay, so far so good. Now, is there a place in our proof where we could get the expression, it's not the case that P or Q? Well, it's not going to come from line 2 because line 2 is the line that we're working on. So we need this line from somewhere. So the question is, where could we get it? So have a look at line 1. In line 1, we have the conjunction of two negations, and the expression we need is the negation of a disjunction, right? So does that ring a bell? Well, it might ring a bell if you remember from the equivalence rules that we have De Morgan's theorem, which is exactly what I just stated. The negation of a disjunction is logically equivalent to the conjunction of two negations. So it turns out that not P and not Q is logically equivalent to the expression that we need to make disjunctive syllogism work to derive the conclusion. So we've essentially, because we found this on line 1, we have mapped out the proof only backwards. So now we have to put the proof together formally using the axioms to justify each of the steps. So on line 3, we'll write it's not the case that P or Q, and we get that by applying De Morgan to line 1. Remember that De Morgan is an equivalence rule, and so there will only ever be one premise, one line number written here, because we're applying an equivalence rule to a whole line or a part of a line, but never more than one line. Okay, so now that we have this, we have the disjunctive syllogism we need. So here's the first premise of the disjunctive syllogism, corresponds to line 2. Now we can see that the second premise of the disjunctive syllogism corresponds to line 3. Or to make that more clear over here, this is the square, this is the triangle of the first premise of disjunctive syllogism. This negation sign negates everything that's in the square, the well-formed formula that is the left-hand scope of the first premise of disjunctive syllogism. So we're entitled to draw the conclusion, everything in the triangle, which is the well-formed formula R or S. So we applied disjunctive syllogism to lines 2 and 3, and because we've succeeded in deriving the conclusion, we can indicate that the proof completed. Okay, so sort of a tactical comment here. This what I'm making notes on over here. This is not like an algorithm where you can, plug in values and basically churn out the proof. Rather, it's a sort of structured way of allowing us to engage in really what is trial and error. I mean, basically, we're just thinking of the different inference and equivalence rules that we have available and seeing how we might be able to apply those to components that are given. So there's nothing certain or magical about this approach. It's really just a way of keeping notes for yourself on what you've tried so that you don't go back and hit the same dead ends over and over again. All right, let's have a look at a different proof now. This proof is P, line 2, not P or Q. Line 3, Q is materially equivalent. That's our biconditional operator. So Q is equivalent to R, and the conclusion we're trying to get is R. So again, I'm going to start with R. It looks like line 3 is the most promising place to get R, but there's really no equivalent. I mean, there's an equivalence rule about the biconditional, but basically it just allows us to break the biconditional down. But have a look at it and see, is there something promising about that? So what is material equivalence? So what it says is that we can rewrite a biconditional as the conjunction of two implications. So we can have P implies Q over here and Q implies P on the right-hand side. Now, does that mean that we're any closer? Well, this was the schema, so if we look at this expression, actually what we need to do is change the Q to R and change the P to a Q and the the P in the schema to R, so you can see that this can be sort of confusing. So instead of thinking about it like this, let's think about it like this. You have something on this side and you have something on that side. So the schema tells you that you can take those components and break them up like this and this. Okay, now filling this in is pretty easy. So the square is Q, square is Q, R is in the triangle, R is in the triangle. So what we can do with this biconditional is basically break it down. And when I say break it down, we can use material equivalence to write this expression. But notice, this is now very easy to break apart because we have the inference rule conjunction. So that's going to allow us to take these pieces apart from each other. And now what we see is, since we're looking to get R as our conclusion ultimately, the R that's here is now in an expression that we may be able to work with, right? So this, let's say this is a premise. Q implies R. How could we derive R from that? Well, think of all of the inference rules that involve material implication. So what should come to mind? Modus ponens. So if we were going to do modus ponens with this, we would need a second premise, Q, which repeats the antecedent, right? That's standard modus ponens. So the question really is, where are we going to get this Q? Clearly, we could get Q from line 2, because line 3 is what this all came from. So it's unlikely to give us a Q when we need to use Q to do something to what's on line 3. But look at line 2. Line 2 says we have not P or Q. And again, when you see an or, you want to think of all of the inference rules and equivalence rules that have or as a major operator. And so what comes to mind to me is disjunctive syllogism. But if we were going to do disjunctive syllogism to this as its first premise, what do we need on the second premise? So now let's think about this. The disjunctive syllogism first premise has a well-formed formula on the left-hand side. In this case, it's not P. And a well-formed formula on the right-hand side. In this case, it's Q. Well, what we want is Q. That's what we need here to do the modus ponens after we break this up and so forth, back up the chain to R. But look at line 1. In line 1, we have P, but because of the rule double negation, we can write that as not P. Now, why does that help us? Okay, look what we have here. If we consider the not P part to be the well-formed formula inside the box for the first premise of disjunctive syllogism, then we have the schema of the second premise exactly right. It's got to have a not sign out here, and it's got to have in the square everything that's in the square here in the first premise. So that's it. Double negation allows us to get what we need here. We can use it with line 2 to get Q. Once we break down the biconditional so that we have this expression and then break it down by simplification because it's joined together by conjunction, then we've got what we need to do the modus ponens step to get R. So that means our proof is basically complete now, working backward. So we're going to run through this in a sort of orderly way. And when I say orderly, I mean a way that's easier for us to read, right? So let's do this. On line 4, let's use material equivalence to rewrite line 3 as Q implies R and R implies Q. And then on line 5, we need to justify. So on this, we use material equivalence on line 3, okay? Now on line 5, we're going to write Q implies R. We're going to justify that by simplification on line 4. So again, simplification works because we've got a well-formed formula joined together to another well-formed formula by an and, a conjunction. So we are entitled to take one whole side out by justifying it with simplification. So now that we have this, we need to get Q. So on line 6, we're going to set up the disjunctive syllogism by applying double negation to line 1. And on line 7, we're going to derive Q by disjunctive syllogism on lines 2 and 6. Okay, so let's see how that works. On line 2, we have the disjunctive syllogism part. On line 6, we have the negation of everything in the square. That's the left-hand scope of the or of the first premise of disjunctive syllogism. And so that allows us to conclude everything in the right-hand scope of the first premise, which of course is Q. So now look what we have. In line 7, we have the second premise of the modus ponens that starts on line 5. And so on line 8, we conclude R by modus ponens applied to lines 5 and 7. And of course, R is what we were aiming for, so the proof completes.